So the goal here is to estimate the parameters W and B. These W and B's for all of these layers that we have. The way we estimate the weights and biases, or for that matter, any parameters of a neural network, is using an approach called as backpropagation. The way backpropagation works is actually quite simple. Backpropagation is built on gradient-based estimation methods. And the reason it is called backpropagation is the way backpropagation works is by backpropagating the model errors down the network. Meaning, we initialize the model with some random W's and B's, any random W's and B's. This is that. So we initialize with any random W and B's, and then estimate my Y which is denoted by Y hat, and whatever error I get, which is simply Y minus Y hat, backpropagate this error down this network to relearn my W and B's, and keep on iterating this over and over until you get a value of W and B's which has minimized this error to the lowest possible. That is what backpropagation means. And backpropagation is, as I said, built on the foundation of gradient-based methods, and it is best understood if we see how a typical gradient-based method works for a single node model, or it is also actually commonly known as a logistic regression model. A logistic regression model is actually a MLP, a dense layer network with only one node. If it has only this node, it is actually a logistic regression, which we might be quite familiar with if we have gone through traditional machine learning courses. Logistic regression will take all the x's as an input and yield my y. Now at this point you may also say, and which is true, that logistic regression is actually quite similar to a perceptron. So logistic regression is a single node neural network, and with logistic regression, the update rule for estimating the parameters theta, and here by theta I mean any of my parameters W or B, the update rule looks like this. Theta t plus 1, where t is my iterator, is simply my prior t minus the sum multiplier eta times the gradient. And if we find the gradient is actually y minus y hat. For some function of y minus, the gradient contains the error y minus y hat. And this was my error. So if we see here, a simple neural network, a single node neural network, which is a logistic regression model, when we estimate parameters there using a gradient based method, what we are doing is we are using the error in the model to update my theta, my parameter. The same logic is extended in a backpropagation approach, in which instead of a single node we have multiple layers with several nodes, but the concept remains the same. There as well we are backpropagating this error that we have here in the model. Now, in the later section of the chapter, we'll talk about each thing we mentioned here, the gradient, and the problem that we face when we are backpropagating this error. We'll talk about the importance of a well-defined gradient, because that can lead to vanishing or exploding gradient, which makes issues in backpropagating the errors. But at this point, it suffices to understand the whole picture of how a neural network, an MLP, works. An MLP at a high level looks like a stack of layers, starting from input till the output, going through multiple layers of perceptrons, and each of these layers are essentially doing some simple mathematical operations to get to a feature map. These feature maps essentially contain the output from this layer, which is processing some arbitrary subproblem of a very large complex problem we are solving here. This feature map will contain the results of those related subproblems, and then these feature maps will ultimately lead us to our final output y hat. With that, our fundamentals on MLP ends here, and then now we will go to our next section of building models.